Welcome to our presentation on data mining and hyperparameter optimization for real estate prediction models. In this presentation, we will discuss how we accessed a hidden archive, past rental apartment listings on Immobilien Scout 24.de in Hamburg, and how we optimized our models for accurate predictions. Let's go. We'll start with an overview of our project. We use data from the website Immobilien Scout 24.de, which didn't have a public API available. We extracted basic features visible in the listing code and valuable features hidden in HTML script tags as nested JSON mixed with strings. The most valuable data included latitude and longitude, the number of images per listing, and listing and unlisting dates. Our project is a regression problem, the target variable being the base rent. We used Python as our programming language and implemented lasso regression and XGBoost regressor as our estimators. We optimized our models using grid and random search and evaluated them based on predictive performance and interpretability. For the extraction and data sources, we identified HTML tags holding key information and looped over past and active listings from 2016 to 2019. We extracted features for each listing using Beautiful Soup, utilized the nested structure of HTML code, and created unique and robust identifiers for each feature. Due to the JSON nested structure not being intact, we had to resort to regular expression patterns for parsing the data. Here is a Python code snippet demonstrating how we used the nested structure of HTML to extract data. We defined a dictionary called all_tags that contains the features, tags, and class attributes required for the extraction. Using it in a way that is shown on this slide ensures that we have a robust and valid mechanism for capturing and extracting the data that we want to capture with each of the combinations shown here. So for example, in order for us to have a robust and unique identifier for feature named number of rooms, that means we have to combine it with the tag that it belongs to in the HTML source code, that is a DD tag, and the specific class, and that one is 24, and then QA minus sigma, and then the rest of this. So this here is an example of the three elements that we defined in order to make it possible for us to extract from roughly 12,000 listings the value that is associated with the number of rooms, which is present in every single listing. Because you can't put a listing on Immobilien Scout without specifying the number of rooms. That is one of the needed features, and as such, there should not be any errors or wrong values captured for this value during the extraction process. So that's just an example of how we did it, and the thinking that we had to do in order for us to create a data set that then can be used as input data for a machine learning algorithm. To extract the data, we resorted to using regular expressions, as shown in this Python code snippet. We defined several regular expression patterns to match the required data. However, there were shortcomings with the patterns used, such as the lack of capture groups and the need for extensive data cleansing and validation to ensure the data's accuracy. We look in detail, we can see that it would have been quite easy to fix the shortcoming related to no capture groups being used. So if we just were to insert, open parenthesis, and here we do a close parenthesis, then we could extract a valid date format that pandas recognizes, and that'll make it easy for us to convert it to any other ISO date format that is acceptable. And as such, it would have been easy to do it during this step and not after we had extracted the data already, because that meant that we actually had to validate a lot. We had to, ensure that there were no. So before we would do any conversion, we had to validate a lot, which we will see later. In our extraction process, we use dictionaries to store and organize the extracted data. We made sure that each variable had one value per row, and we handled invalid values using try except blocks. Missing values for optional features, such as whether the listing offers some sort of car parking, are not invalid and were translated to none. For many others, a pandas compatible string NaN was inserted. It was very much a case, you had to evaluate each variable separately and assess what the meaning is of a missing value, because the JSON data in the HTML script tag, it actually showed that whenever there was none found in the source code visible on the listing page, then it would actually translate that for whoever uses the API that they have internally to none or 0. So, for example, if you had something like elevator was a feature, and you would find a yes if there was an elevator, but most of the time you would just find a missing value. But looking at the data was given in the JSON part, in the parsed JSON data, it became clear that whenever there was a missing value, we checked the indexes, and the indexes they were aligned like 100%. Whenever there was a missing value in the visible code, that meant that it would translate to doesn't have a balcony, or pets are not allowed. And it wasn't so important to use that in the context, because otherwise we would not be able to really understand what a missing value for a specific variable actually means. And that would have meant that we would have lost a lot of data simply due to a lot of missing values, when actually it's just that not a lot of listings have elevators. So it's always important to look at the context and to try and analyze what a value of a missing value actually means. Error handling played a crucial role in our extraction process. For example, when extracting the latitude value for a listing, we used a try except block to catch any attribute error that might occur, appending NaN as a placeholder when necessary. Now, it is important to note that we only used the attribute error for the except part of the try except block, and we did that to still get notified if some other error is occurring that we do not have understood yet, or that we don't know of yet. So we could have, of course, used exception as E, with the short line, with the alias, and then any exception would just trigger it to append NaN. But not all exceptions would be actually, as bad that we couldn't change our algorithm that we used for the extraction in order to get valid entries for occurrences, where if we just used any exception, we might just get a lot more missing values. But that is not because they were missing. That is because we had a bad structure for extraction when it comes to that feature. So it's always important to keep that in mind. We had to clean and validate the latitude and longitude columns in our dataset, as the unique values method didn't work, with almost as many unique values as rows. We used string methods and regular expressions to extract valid parts of the data, and raised errors when performing type conversions. We also checked the number of missing values before and after the cleansing process. All this together was a harness that we created to ensure that from the data that is valid by, I don't know, like the core is valid, that we would be able to cleanse the data and validate, and that would work for most of the data that might be challenging or might not be, it might not be obvious for us how to work on that data in order to create features that could be vital for the machine learning process, that might be of one of the highest ranked features when it comes to importance. And as such, it was so critical to get that step right. Here's an example of how we applied our cleansing and validation techniques to the latitude and longitude columns. We transformed and cleaned the data to ensure that each pair of lat and LNG values was valid. Now we can see here how the data looked as when we first captured it, and when we start the cleansing process. And you can see that there's a lot wrong with this. Like each value is it should just be this part here, basically, the floating point number. And you can see that there's a comma at the, like, after the last digit. And for the latitude and longitude values, it is of very high importance that you do not truncate any of the decimals, because they matter a lot when it comes to like using the GPS value to mark a specific location. So it's very important that you understand your data, and we try to keep that intact in order for us to create a very, very solid basis for feature engineering. And it's not just feature engineering, it was enrichment. We used other data from other sources, and that was only possible because we had solid values for the GPS column, for the tuple that is of the two. Now, our goal was to create a GPS column where each pair of latitude and longitude, given by lat and LNG values, represented a valid GPS location. We ensured that the index values with missing data were identical for both latitude and longitude columns. We used the assert statement to check for this. But it's worth noting that in production code, it's better to use exceptions instead. Here we use syntax for pandas to work on a data frame, to validate that all the index values of missing data in each of these columns, LNG and LIT, are identical. As a sidebar, here's an example of using exceptions in Python to validate date formats. We define a function called validate_ISO_date, which checks whether a given date string is in the correct format. If the date format is invalid, it raises a value error exception. So this is a very basic definition of a function that can be used for validation. By using this, we were on the safe side. If it passed this test, then we knew that pandas would recognize it, and then we could use that date to unlock the powerful features that pandas has for date and time objects. For a GPS column, we perform type conversion to float. Create a new column with ordered tuples of latitude and longitude given by lat and lng, and applied the point function to create geometry objects. The point function will raise errors very quickly because it needs the data to be in a very specific format. And as such, it is a good built-in validation tool. After processing, our GPS column contained geometry objects as shown in this sample output. Each row now had a valid GPS location represented as a point object that we then used for extensive creation of new features and evaluation of these new features with regard to their importance to the accuracy that our estimators were able to output given different sets of the enriched and newly created location-based independent variables. Now, feature creation allowed us to enrich our data set with additional information. We assigned street noise levels to each listing using external noise data, determined the neighborhood status level for each listing, and computed the distance to the nearest subway or suburban train station from each listing. Usually the preferred transport method that is available in the area that you live in usually is subway first because it's the fastest. If you have a station nearby, and if there is a station nearby your destination, of course, and then suburban trains, they don't get the problem of congested streets. They have their own paths that enable them to be much faster, and as such, these two methods of transportation should be, or usually are, the first and second best options. And so we use both of them together because so there might be listings that are on the outskirts of Hamburg. I mean, there was not a single listing that was outside of the federal state of Hamburg. They were all inside of it, and as such, there might be some listings that don't have access to a subway, but they still might have access to a suburban train station. And we didn't know how much of a difference that makes in terms of the base rent, which was the target variable for us. So that's a little background info that reveals some of our thinking that we had to do in order to create this feature. For the number of images per listing, we converted the values to integers and removed outliers using summary statistics. For example, we capped the number of images at the maximum allowed per listing. Now, for the days listed feature, we extracted date parts from a string, converted them to timestamps, and created time delta objects, which is a pandas specific data type. We filled missing values and invalid rows with the mean or the median time delta and truncated time delta values to match the level of the source data. In the example, down to the day. Now, most of the time it wasn't too difficult to fill missing values because the way that the algorithm went through the pages, the 600 pages, page 1, and then would go to like 600, all the way to 600. But The number one is that actually has the most recent data that is still listed. And now, as we go back, well, it would go further and further back in time. So it would go to, like, 2017, the 1st of February. And then if we have a missing value for the listing that comes after that one, and then usually, I mean, it was actually never the case that we didn't have a value that is like, that comes afterwards, that has a valid date or listing date. And what we then did is, because we knew the chronological order, we knew that we could just use the same value for the listing as they were just the way that, the algorithm was capturing it. It was just in that order. I mean, it's not the same for the day when it was unlisted, because that is not given the previous listing and the next listing. That it could be way different, because the next listing could already been unlisted 2 days after it had been listed, and the one before could be unlisted 4 days after it had been listed. But you don't know for the one in the middle when that one was unlisted. In a model training phase, we experimented with different representations of the data, which is commonly referred to as feature engineering, such as using the date listed, unlisted, and time listed, which is just the time delta. We also added more views to the existing data, such as year, month, day, and day of the week. In our model training, we found that latitude and longitude values enable spatial autocorrelation for the XGB regressor. The GPS column was less useful to the model. The features time_gap and number_pix, which means number of images, ranked high in importance, as shown by the F-score. Our model explained about 92% of the variance in the test set using the XGB regressor. The last one was slightly lower, was 87%, which is still very good, but is less than what we achieved and with the XGB regressor. And there was nothing like spatial autocorrelation, which was apparent from looking at the coefficients of the lasso model. So the F-score, what you have to keep in mind is that it is a relative score. It is not absolute. So you can only compare the importance. So let's look at the next slide for that. So yeah. Whoa. So yeah. So here, for example, so we have the status. So this was also a location-based feature that we added. And this one has an importance of 816. Now you can relate that to the importance of on which floor the listed apartment was in, and you can say that is double, like, from that. But you can't say that because so here there's 1,000 difference. You can't do that with the F-score, that you can start comparing different feature sets most of all. So because the values, they're all relative and they're unique to the estimator that you trained and the features included. But what we can see here is that the latitude and the longitude, they both had basically the same value, along with so that's kind of interesting, because that means that, I mean, looking at we looked at the decision tree structure of the finished model, and we tried to analyze how it split based on latitude and longitude values. And we could see that it would split in conjunction. It would use both values, and then if it is above some latitude value and you look at the longitude value, so above some latitude but below some other latitude value, and then you combine that with the longitude value. Because interestingly, we used, as a visualization, we we're able to detect that going from the east of Hamburg towards the west, it means that the rent as base rent per square meter, it increases steadily. So that is something the creation and the extraction of the latitude and longitude values enabled us to do. So ancillary cost, that is that what is added to the base rent to give the total rent, it's difficult to analyze. They can change a lot. Yeah. So it depends on how the heating works, if it's oil, if it's gas, for example. And so this is kind of a difficult one, but nonetheless, it actually ended up being important. Square meters is just how many square meters a rental apartment has, basically. And then we use the time gap, which is what we use from the listing and unlisting values. And the number of images was also important. And the floor, and then we have the download speed. There's another value that is kind of, I don't know, it's kind of weird to analyze because they only give this value for certain listings on the platform. And then they only assign a value to a listing if you can use the provider telecom or your internet. So it's kind of 3 or 4 unique values only for this variable. But nonetheless, it seems to have helped the model in predicting. And so this feature here did not. So this is if the walking distance, the walking distance we researched was approximately equivalent to 0.6 kilometers for distance between the listing and the underground station or the suburban train station. And that is including the average of, that you can't go straight to that station, but you have to walk around buildings, right? And you have to follow streets, and it's not always optimal. So the 0.6 is, if we didn't take that as a straight line, and then including, so then the threshold was about 15 minutes, and so if it's longer than 15 minutes for you to walk there, then it's not a viable station. And then we would say smaller, 0.6, no. So this was an aggregation, and we used others to try and give the model more specific details, which did end up improving the results. A company in the US, a US real estate corporation called Zillow, uses a similar process on a much larger scale for their data analysis and predictions. You can find more information on their website at, just follow this one here. Now, so we did our project in 2019. Back then, there was no such feature that that there was no corporation known to us, at least, that used something similar like that. But they seem to be rather successful, combining a lot of features and analyzing and predicting the values of sales. Mainly, it's just house sales. Yeah. Now, our project has several limitations, such as performing data extraction only once, the extensive use of regular expressions not being feasible for high-volume data, and dealing with a relatively small amount of data. So preferable solutions for these limitations include using incremental loading techniques, ensuring the ETL process meets business requirements and satisfies data needs of other departments, storing structured data in traditional DBMS like MySQL, storing semi or unstructured data in NoSQL databases like MongoDB, and using data validation tools like Pandera. Now, Now let's see how this could be implemented. Create a reliable and scalable ETL process. Examples of solutions using AWS services include AWS Redshift for database storage and AWS EC2 for on-demand computational resources. We can use EC2 for both data transformation and loading, such as through RESTful APIs. Now, if we're looking at the literature, here's a selection of useful literature. So one useful resource for learning more about data mining is the textbook Data Mining, Concepts and Techniques. And this book covers various aspects of data mining, including data pre-processing, extraction, cleansing, validation, and enrichment. So what we have done, but they give the tools, to make it on to use it on a much greater scale in a business environment, on a large scale one. Now, another relevant paper is Data Cleaning, Problems and Current Approaches by Ram and Doe. This paper provides an overview of data cleaning problems and current approaches in the field. Now, the guide, CRISP-DM 1.0, is a step-by-step data mining guide by Chapman et al. And introduces the cross-industry standard process for data mining, CRISP-DM, that is, which is a widely adopted methodology for data mining projects. And it's definitely a resource if you want to learn more about data mining. That is a very good source to consider. Now, last but not least, we have another relevant paper called An Overview on Learning from Data Streams. So this one is very much just the focus here is on data streams, which is data that comes in a very, very high at a very high rate, and that can cause a lot of problems because traditional methods used for data mining that do not use techniques like incremental loading, for example, among others, are just highly challenged or cannot be used at all. So this paper provides an overview of learning from data streams, which is particularly important in the context of real-time data processing and analytics. Yes, so these resources we handpicked for you to get a deeper understanding of the problem and of challenges and solutions in order to deal and with data that has to be mined for important insights. And we must not forget, we usually in a corporate environment doing data mining, we want a competitive advantage compared to our rivals, to other companies that operate in the same field. So thank you very much for taking the time to listening and watching this presentation. And if you have any questions, any concerns, or if you have anything to say, basically, just leave a message in the comments and I'll get back to you. Thank you very much.